WTW1, but one of the double series. To the best of my knowledge, we are somewhere deep inside chapter 2, trying to understand what's happening with stationary models that can be used for double series. I think we will be finishing this chapter today, and then we can move on to some models for non-stationary double series. So we last week on Thursday ended busy with AR2 models, and specifically we were talking also about partial order correlations. Just maybe a quick recap of what we have done. We are looking at a special class of time series model that's very popular in modeling called ARMA models, autoregressive moving average, and we are only focusing on lower order models. So I will not at all expect you to do any derivations or theory feats when we have P or Q, the orders for the autoregressive part or the moving average part large. It will be an AR1, which is a pure autoregressive model, or an AR2 pure autoregressive, or MA1 pure MA, or MA2, or ARMA11. Those are the 5 models that we are focusing on. In practice, we don't use higher order models. There end up to be too many parameters. And what also happens is, if we, for example, scroll down, if you go and look, well, I don't have anything here, but if you go and look at the lecture notes, of course, don't put any on the slides. If you go and look here in the lecture notes, and scroll down in a bit, you can see better. And then scroll down again. If we go and look, for example, for a for AR models. If we go and look at an AR1 model, the autocovariance function is very straightforward. Even a bit inside the text, but there it is. So look around there. For an AR1, the autocorrelation function is just equal to that autoregressive parameter applied to the power graph. So very simple formula for an AR1. But when you get to AR2, things become much more complicated in that we have to calculate recursively, as is shown here. Although the general linear process representation, and when we get to the order correlation function, there, for example, is the formula for rho 1. That 1, it depends on phi 1 and phi 2. And if you go to higher order lags, then you need to start calculating them recursively. So rho 2 is phi 1, rho 1 plus phi 2. And then from that 2 onwards, you need to calculate, well, actually that 1, it will become the same formula. But you need to go and calculate these autocorrelations recursively. So the expressions become just far more complicated when you get towards high order models. So in general, if you have an ARP model, then go down there, that autocovariances. Down here. A lot of parameters just complicate matters. And the same thing with the autocorrelation function down there. So the focus definitely on AR1, AR2 in terms of autoregression. And likewise, MA1, MA2 for reductions. Now, most of the time series models for ARMA, in fact, nearly all of them, are used to explain irregular variation. So we explain irregular variation with ARMA models. We will get to models not today, but in this week maybe this week, that can be used to explain seasonality. So seasonal patterns. We will get to models that can explain an upward trend. Specifically, we will look at linear trends. We will also today see, and that we're going to show now, that there's a very special ARMA model that can be used to explain cycles. A very special one. It's an AR2 model. But in general, let me just stress this very clearly. ARMA models we use for irregular variation. We have irregular variation. But the AR2 is a very unique special model that if we pick our parameters carefully, then we can end up having an AR2 model which can explain cyclical behavior. And I will illustrate that soon in the theoretical one. But first what we need to look at, don't think I included it in my slides, maybe it's there, yes there it is. This is, for the AR2 process, a very important triangle. Because for an AR2 process to be stationary, these are the three conditions or restrictions, not really conditions, the restrictions we have to place upon the parameters of that process to be stationary. So for an AR1, there's just one parameter, phi, and if that phi is between -1 and 1, we have stationarity. Very straightforward. When we have an AR2 process, with our two parameters, we get three conditions. We need to have that the sum of the two parameters less than 1. The difference between phi2 and phi1, very importantly, phi2 is put first, not the other way around. That difference needs to be less than 1. And then phi1 is on its own unrestricted. Phi2 is the parameter that is restricted to between -1 and 1. And if we go and sketch these three conditions, we get this triangle. So if we look carefully, we have here a line phi2 equal to 1 minus phi1. Now, sorry, on this axis, we have phi1, our first order regression parameter, and in this axis, we have phi2. And this triangle gives us the values of phi1 and phi2 for which we will have stationarity. So this line that has been drawn here, phi2 equals 1 minus phi1, that is the line linked to basically what we have here, this first condition, that the sum of the phi's must be less than 1. So this is the border. If we go below this line, so lower and towards the left, then we have stationarity. If we are to the left and lower this line. This line here is phi2 equal to 1 plus phi1. That is linked to the second restriction, where the difference between the parameters must be less than 1. So, if we are below this line and towards the right, we satisfy that second condition. And the third condition is that phi2 should be between 1, that is the line there, and -1. So if we add the third condition, this restriction, then we end up with a triangle. And this triangle gives you the stationary region of the AR2 process. So any combination of phi1 and phi2 lying within that triangle gives us stationarity. So let's say that phi1 on its own is not really getting restricted, but in a sense it does get restricted, because if you pick any phi1, it will not work, because you need to fall within this triangle. So we cannot really get phi 1 to be more than 2 or to be less than minus 2. Because if we pick a phi 2 of say 3, then of phi 1 equal to 3, then there's no corresponding phi 2 value which is going to allow us to get these two conditions as well. We make, for example, phi 1 equal to 3. Phi 2 will have to be so small in negative sense that it will fall outside that boundary for a special phi 2. So in a sense, phi 1 does get restricted, but in general, we don't restrict it when there's no condition for phi 1 itself. Phi 1 together with phi 2 has to adhere to these restrictions that we have there, those three restrictions. So this is the triangle for stationarity for AR2. For AR3, AR4, AR5, things become a lot more complicated because you have a lot more autoregressive parameters to be concerned of. So I will not ask you for stationarity for higher order AR models. I will not ask you anything about that. Now, apart from the triangle, there's another curve that has been drawn here. This dotted curve here, which is the curve for phi 1 squared plus 4 phi 2 equal to 0. That curve comes from, going to the lecture notes, where it is discussed for the AR2 process, stationarity. Here you just see, scroll down. Here we have stationarity of AR2 processes. Here it gets explained what are the conditions to have stationarity for the AR2 process. So if you take the characteristic equation, which we obtain from writing the AR2 process as or in terms of the lab operator, and then replacing the L's with X and setting that polynomial, that parabola equal to 0, we get then two roots, and inside these roots, there we get the square root of phi 1 squared plus 4 phi 2. Now, these roots will not always be real numbers. If that square root part is less than 0, then we get complex roots. And that is what is, just show it here because it's here as well. That is what's highlighted by this. If we inside here less than 0, so below that parabola, that's all there, then we get that our roots that we will take will be complex for the AR. If we are above it, then we get real roots. So combinations of phi 1 and phi 2 that lies here in the triangle, but above that parabola is where we get real roots. You will get real values for the roots. So when we get combinations of phi 1 and phi 2 in here that are complex, then it is when we start getting some rather interesting and strange autocorrelation patterns for the AR2 process. And that's what I want to show you. So do not be concerned about the code you're going to see next. I will not expect you to do this code. What I want to illustrate next is I will, in any case, I'm going to upload for you this code. I will upload it on pickup for you that you have it available. Because it's not in the lecture notes, so this is something extra that I'm doing now. But I need to show you, want to show you a special case of AR2 processes. So what I'm doing in this program, I'm not simulating any data. So there's no simulation of data happening here. No data simulation. What's happening is here is that we're going to calculate theoretical autocorrelations. Sample autocorrelations, we are SAS, typically SAS, to go and use the RIMA and see them and calculate for an observed series, for the simulated one, sample autocorrelations. Here we want to calculate theoretical autocorrelations, which we then want to go and plot. I want to visualize, see what's happening. So I'm going to use the IML procedure, which you might or might not have made before in your academic statistical career. procedure, I'm specifying that I want to calculate the theoretical autocorrelations up to lab 34. And then I'm going to specify some correlations of phi 1 and phi 2. So I'm going to pick theoretical AR2 models. Now if I make both my phi 1 and phi 2 0, then my heading is wrong because this is then not really an AR2 model. This becomes a white noise process. AR2 with both autoregressive parameters set to 0 is basically a white noise process. You reduce your AR2 to white noise. And what I'm then doing here, I'm creating a vector with missing values in which I want to store the theoretical autocorrelations. And then with a do loop, I'm going to calculate using the formula for the AR2 autocorrelation functions. I'm going to calculate the theoretical autocorrelations. So that's what's happening inside this do loop with some of these statements. Fortunately, the formula are in such a way that even though that I have white noise, because my true plots are 0, those formula will still work because the formula will reduce towards basically 1 at lag 0 and 0 everywhere else. When my lag is 0, then my theoretical autocorrelation is 1, and at all the other lags, I substitute in 0 for phi 1 and phi 2. Basically, I'm going to get 0 for the autocorrelations. And then I'm adding lag from 0 to 24, and I'm creating a data set from this matrix, which I'm writing all these autocorrelations to a data set, because I want to go and plot the theoretical autocorrelation. These correlations for the AR2 is technically white noise. I want to plot against the lag. So I'm not going to put the parallelogram now. The parallelogram is the sample autocorrelations. I'm going to put theoretical autocorrelations here. That's what I will do. So you can use a gplot function where the option becomes for the plot not I equal line or I equal join, sorry. We're not going to join the values. We're going to create a plot that they call a needle plot where we're going to make the width quite wide, 7, and that will represent for us the theoretical of the correlation. So let me run all of this and let's see what we get. Hopefully it works. Nice. Hopefully it doesn't take too long. Well, that's a rather boring plot. But it's a great plot. What I've got here on this axis here now, the lag, 0 up to 24. And here I have my theoretical autocorrelations. So it's theoretical. Cannot be more than 1, it cannot be less than -1. And because I've basically done it for white noise I have at lag 0, the autocorrelation will be 1. And at all the other lags, theoretically, will be 0. So at least my formula is working for white noise. My heading is wrong. Sorry. Let me clear it immediately again because I see my heading says theoretical autocorrelation AR2. This should be white noise. That is action. So let me try again, run it again. And there I got it now. That is the theoretical autocorrelation of white noise. 0 anyway. So it gets rather boring. Let's see if we can get something a little bit more exciting. Let's go and let's make phi 1 equal to, well, let me just do this first because it's got to change now. Not going to be white noise anymore. I'm going to do it now for not AR2, but let's go to first AR1. So for AR1, what I'm going to do is I'm going to make my phi 1 0.5. And I'm leaving phi 2 to be 0. Now I'm starting to get slightly more exciting patterns. This is now an AR1 where I've made my parameter value 0.5. So now my theoretical autocorrelations is defined as, you can go and look in the model, for an AR1, we get, for an AR1, it's AR1, then we get rho k equal to 5 to the power, okay, this is for an AR model. So I've made 5.5. So at lag 0, I get an autocorrelation of 1. At lag 1, that is 0.5. That is 0.25. 5 squared. That is 5 to the power 3. So I think it's 0.125. And so we get that these autocorrelations are all positive because I think 5 to the half. We get exponential decay in our autocorrelation function. So we have a shortening of the process. That's shortening. If I make my phi slightly larger, so if instead of 0.5 I make it, this may be 0.8, and run it all again, then I notice I still have exponential decay, but because that correlation, or that parameter is now getting closer to 1, the decay is a bit slower. Okay, slower decay towards 0. But still, all these other correlations must be positive, theoretically, because my phi is positive. 0.8. So now I have there 0.8, 0.64, and so on. If I make my phi smaller, so suppose I make it, let's say 0.2, then very quickly I don't even see any red bars there. Very quickly all the correlations goes towards 0. All these are examples of shortening. What if I make my phi negative? Well, we talked about this before already. Make it 0.8 again, but negative 0.8. And run it. Now I get alternating pattern. That at odd lags 1, 3, 5, 7, 9, I get my autocorrelations negative, and at the even lags 2, 4, 6, 8, and so forth, my autocorrelations are positive. Still, the magnitude decrease towards 0 very quickly as my lag increase. So these are autocorrelation patterns for AR1. Now what happens if we have AR2? Let's go and see. So we have the formula for AR2, and that's what I've typed in here in the code. But what happens if I have different values for AR2 processes? Suppose I make this now 0.5 and I make this 0.4. I have to pick now, and this is important, for this formula to work. Those formulas are for stationary AR2, so I have to be very careful that I pick values for phi 1 and phi 2, which are now inside this triangle. I cannot go outside of the triangle. I pick now that phi 1 equals 0.5, so there, and 0.4, so that is somewhere there. So I will get real roots. My roots, if I were to work out the roots, will be real. 0.5. And now we're going to see something that is a little bit unfortunate, although interesting. If I pick these, I just need to make sure that says AR2 and this says AR2. Well, then if I stick with this and I run it, come on, also difficult to calculate. That is the autocorrelation pattern I'm getting, theoretically, which looks very similar to, I don't know if I have it still. Oh yes, there it is. Although a little bit quicker, but it looks very much like the AR1. Although I now did it for the AR2. So this is a slightly problematic case that we now have. Although we have two different models, AR1 and AR2, the theoretical autocorrelation pattern, very similar for this AR1 process and then for this AR2 process. Here maybe the decay is a little bit slower. But what I'm trying to tell you, show you here is, remember it's not enough theoretical, but if we had for an observed time series, we cannot use the autocorrelations to identify the order of an AR model. It's unfortunately not possible. That is why we use partial autocorrelations that we talked about last.
So when you want to identify whether it's an AR1 or an AR2 that needs to be worked with, you're going to make use of partial autocorrelations. Very importantly, for identifying the order of an autoregressive process, don't use the autocorrelation function, we use the partial autocorrelation functions. Okay, let's look at a few other patterns we might get. So I've taken 0.5 and 0.4. Let me make this, for example, 0.2 and 0.7. Run it again. And we start to get kind of different patterns. So this is 4.2 and 0.7. Let me make maybe both of them negative. I just have to make sure that they don't get a pattern that's looking like that. So some of them are now negative, some of them are positive. So I'm starting to get that my autocorrelations start to look differently for the different combinations of 5 and 5. And let me do maybe one or two more. Let's make this one 1.2. And run. And this starts to look rather strange and interesting. Because here we had just basically all autocorrelations positive, decay to 0. Here was the same thing, and for both these examples I used positive values for both phi1 and phi2. And then here I made them both negative. Here I made the first one 1.2 for phi1 and for phi2 minus 0.7. And it seems that there is a sort of cyclical pattern happening in the autocorrelation function. Let me do maybe another one. Let's make this, instead of 1.2, let's make this 1.5. And again, looks different from this, but a similar kind of thing that we are starting to see here, a cyclical pattern. So yes, we get that the autocorrelations gets closer and closer overall towards 0. We get decreased towards 0. But now it's sort of with a cyclical pattern. Let me maybe do one more. I'll make this 1, I'll make this 1.7 and 0.9, and the final one I'm doing, and this really shows us we have a cyclical pattern here. Or as they refer to this in time series analysis, it's a damped sine wave. So it's like a sine graph that we are getting, sine pattern, trigonometry, but it's damped in that the amplitude or magnitude of these autocorrelations become less and less and less. Maybe we see here a little bit better. That there's like a cyclical pattern in here, but it decreases in absolute value towards 0. So the cyclical pattern disappears. This is a very unique property of AR2 models. So you're not going to get this kind of pattern with an MA2 or an MA1 or any other ARMA model, but a pure AR2 model. And specifically, you get this kind of pattern. I don't know how many of you paid attention to how I picked my phi1 and phi2. Go back here. I've picked phi1 and phi2 values in such a way that I've made my phi1 and phi2 that they are from going to, what we have here, coming from here, underneath that dotted parabola, where the roots are negative. So when you have an AR2 process, and your phi1 and your phi2 are taken to be, in this case I've taken, for example, phi1 at 0.1.7, so somewhere there, and then phi2 in such a place it has to be inside the triangle, so it can't go outside, and I make sure that it is down here, below that dashed curve. Then I have stationarity, and I get that my autocorrelation pattern exhibits cycles. cyclical behavior. So the AR2 model can be used not just for irregular variation, but can be used to explain cycles in time series. So in a later assignment, to come quite a bit later, you will be asked to use the AR2 model to explain that cycle that hopefully you have observed by now in the Sunspot data. The annual Sunspot data cannot have seasonality. Why not? Because annual data cannot exhibit seasonality. But you can have a cycle, and that time series exhibits a cycle. That cycle can be explained with an AR2 model. AR2 model can be used to explain that cycle. That is the AR2 model for us. Any questions from your side about AR2? Unfortunately, the derivations for the AR2 they are not nice. I'm the first to admit that. So, I go up here. Specifically, if we go up here again, for the AR1, the derivations are straightforward. But for the AR2, to write it, for example, as a general linear process, this is not a straightforward task in that, well, you basically have to go and find expressions for those omegas, and we end up having recursive expressions. Omega 0 is 1, but then omega 1 is phi 1, and then from omega 2 onwards, you calculate them recursively. And then, because we only get the recursive formula, we cannot use the nice formula that we had before for the, not nice, but we expressed had expressions for the variance and autocovariances. We cannot actually use them to get the autocorrelation function for the autocovariance function for the AR2. So we have to do it from first principles, and that's what's shown here. So we have to get basically gamma 0 and gamma 1 and solve them simultaneously to get expressions. And these are not nice expressions. For an AR1 or an AR2 already, I mean, this is a horrible formula that we have there for the variance because of those two parameters. So you can imagine when you're going to get to an AR3, AR4, or the formula just becomes worse. So we're not going to look at the high order models because they're also not really used in practice. Practice AR1 and AR2 gets used. But yeah, that is the variance, that is the lag 1 autocovariance, and then the Rivik formula that we have there. Please don't memorize it. If you need it, I will ask you to derive it in the semester. Or I will just give it to you. What I sometimes do is I say, given that gamma 0 equals, show that gamma 1 equals, and I ask you, yes. So I don't ask the whole group for 23 marks. I ask just part of it for 5 marks, something like that. So, yeah. From that 2 onwards, you calculate them again recursively, and then for the autocorrelations as well. You calculate them recursively. So that's the autoregressive formula. Now, people used to work with AR3 and AR4, and they didn't like it a lot, the high order model. And then somebody decided to show that something very interesting happened. Instead of using an autoregressive model with high order, you can actually work with a mixed ARMA model. So going down, we can get, scroll down, mixed ARMA models. And we will only look at the ARMA 1-1 model. So the ARMA 1-1 model now has the lag autoregressive term, the ZT minus 1, and then a lag white noise term. And by using that lag white noise term, which is one extra parameter of theta, what happens is that allows you to avoid having to instead work with an AR3 or an AR4 or an AR5 higher order models. So it is still a model with a few parameters to work with, but it gives us more flexibility. So instead of looking there, it might be easier to look here. focusing on with the ARMA, we will be looking at ARMA 1-1. So in general, you have an ARMA PQ process with P autoregressive and Q moving average terms, but our focus will be on ARMA 1-1 models, where you have one lat Z and one lat Y twisted. So you don't really need to put subscripts there, phi 1 or theta 1, because there's for each of them just one parameter, one autoregressive and one moving average. Now, autoregressive processes are always invertible, but we need to restrict the parameters for stationarity. Moving average processes are always stationary, but we need to restrict the parameters to get invertibility. When we work with ARMA models, you have to restrict both phi and theta. So, I need to read the slides, but I have it in the lesson notes because it is important. For stationarity of an ARMA 1, phi needs to be restricted to between -1 and 1. So that is the restriction we have for an ARMA 1-1 for stationarity. And to have that the ARMA 1-1 is invertible, we restrict theta to between -1. So for stationarity and for invertibility, those are the conditions. Remember, what is stationarity? Stationarity is that the mean and the order covariances are not functions of time, do not depend on time. So the mean stays constant over time, the theoretical mean, and the variance and the order covariances do not depend on time, so the variance stays constant over time, and the order covariances only depend on the lag k, not on time itself. So the order covariances only depending on the lag. So what we mean by that is gamma 1 is not the same as gamma 2 or gamma 3 necessarily, but the covariance, if we look between two consecutive variables, Z1 and Z2 is the same as between Z5 and Z6. So the covariances at a specific lag constant. Invertibility is where we want a one-to-one relation between the parameters that have an effect on the autocorrelation function and the autocorrelations. We want a one-to-one relation. So for that reason, we then restrict the parameters. So for the ARMA 1-1, theta between -1. So as with the AR1, AR2, MI1, MI2, we need to be able to express this model that we have there as a general linear process. So to do that, we go and write in terms of the lag operator, and then we set it equal to the expression for the general linear process, and the mean is the same as for the AR1, because the mean level, when there's autoregressive components in your ARMA model, like AR1, AR2, ARMA 1-1, the mean is not dependent on the thetas, well, the lag, the thetas for the lag white was terms, it does depend on the intercept, and then the autoregressive parameter. So that is the mean for the ARMA 1-1, and then we get that these terms, basically what's in front of AT there, is equal to this. So from this, we can go and work out what are the omegas for the general linear process representation. And here they are summarized. So we get a general formula, we can again work out our general linear process coefficients recursively. Once you have a particular one, you can calculate the next one because you basically multiply by 4. That is the general formula that we have for the general linear process coefficients. So that is the ARMA 1-1, stationary ARMA 1-1 general linear process coefficients. And then to get the variance, we can use the formula that we have for the general linear process variance. That formula can be used. We need to do a little bit of simplification happening here, but you basically quickly go and write down, if you want the variance of this, this is the formula that you get for the variance. So 1 plus, and you just basically work out all the variances, and those coefficients in front of the white noise terms you need to square. Why are we not concerned about covariances here? Because white noise is uncorrelated. So the covariance between 80 and 80 minus 1, or 80 and 80 minus 2, between 80 minus 1 and 80 minus 3, all the covariances equal 0. So that's why the variance is rather straightforward for me. And we can get gamma 1, gamma 2, and so forth as well. So the covariances at different lags. In general, we get that is the formula for the autocovariance function. And then, why we don't really are so concerned about autocovariance is we actually want the formula for the autocorrelations. So that's what's given here. This is the formula for row 1. And again, in general, if you want to calculate higher order autocorrelations, you can calculate them because. Now, something important. When you have a peer MA model and you want to identify whether it's an MA1 or an MA2, then you use the autocorrelation function. So I'm saying this thing again. When you have a peer MA model and you want to know, but is it the MA1 or is it the MA2, use the autocorrelation function. If you have a peer AR model and you want to know is it AR1 or AR2, then you use partial autocorrelation function. If you have ARMA model, you cannot identify the order of the AR component and the order of MA component together using partial autocorrelations and autocorrelations. I've seen many people trying to do that. It does not work. So I'm stressing this. Please never try and attempt to do it. I even get master students that try to do it. Mostly they come from other universities, I shouldn't say that. Luckily people that come from UP, they don't do that. You cannot use, for ARMA models, the AR or the autocorrelation function to identify the MA part and then use the partial autocorrelations to identify the AR part. It does not work. We will see in a later chapter, I think it's going to be chapter 4, how we can use other identification methods to identify the orders for ARMA models. So we will get to a way of doing it. But please don't try and use autocorrelation, partial autocorrelation functions when you have mixed ARMA models. They can only be used for peer AR or peer MA. And I will now show it to you when we're going to look at the simulated example. So we'll go here into SAS. Maybe we should take a break first. Let's take a break. Let's see 17 past already. So when we come back, I'm going to show you an example where we're going to simulate from an ARMA series. And I will show you something interesting happening if I'm going to change select the parameters in a bad way for that ARMA process. But let's take a little break. We can start again, well, half